All right, everybody. This is Falling Sphere video part 2. I actually mistakenly stopped the last one. I didn't do that on purpose, although I guess it was getting pretty long. I actually accidentally hit the stop button, and it was less painful just to make a part 2 rather than to try to append to the earlier one. All right, so this is where part 1 left off. We've just created our control panel. And now we're going to create the columns we're interested in. So, of course, we're going to have a time column. Right? So we need a time column. We are going to have a position column, a velocity column, and now let's include an acceleration column. How about? Right? I'm going to make this look a little neater. I like to center things. But also look, the acceleration's too long. It's leaked over into column H. So if you just go up, see if you move your arrow up here in between the G and the H, it changes there, and you can then drag it and change the width so that column G is a little wider. So then I'm going to highlight D, E, F, and G, where I've defined the 4 columns I'm interested in, and then just go up and do this little centering thing. It just makes it look nice. That doesn't change the content, of course. All right, so here we have all our control panel. Here's our columns now, and it's time to start populating the columns. Right. The first thing we're going to do is just set the initial time equal to 0. Right. Just put a 0 in there. Okay. I think that's a 0. Yeah. And of course, we want to populate this with times which are all from row to row. Each new row represents a new time, and every successive time we want to be separated by that constant dt, right, delta t. So, as we've done in the past, let's assign the second, this is the next time step, let's assign it equals, now I'm just going to program it properly, I'm going to choose the previous time. So the time at the next time here will be dt, the previous time, plus, or sorry, not d2, sorry. It points to what I selected. And then I want my name, dt, or the variable, delta t. So I'm just adding to the previous time what I've defined as delta t here. Okay. Remember now, you highlight the one you've just programmed, go over to this little square, and we're going to drag it down. How far down to drag it? I would say just take it a whole bunch. It's going very slow for some reason, probably because I'm recording this and my poor little laptop is maxed out. The video card, I believe, is maxed out. So let's just wait for a few. It's just going to go slower than it usually does. So let's take it down, I don't know. This is probably good enough. We can always drag it down further if we need to. All right, that's good. Okay, so let's look at what we've done. I drug it down, I don't know, 1,000, 4,000 some. Go back up, and you'll notice now, and I always want to point to the analogies between what we're doing here. This is not a programming language. This is, I would call Excel a programming tool, though, or a computational tool. It's not really a programming language, but keep in mind, every one of these times is a discrete point, and they're all separated by the same delta t. And you'll notice if I highlight one, even though we're not concerning ourselves too much with this row number here, every one of these values is indexed. See that? So if I start out, just so happens we index the starting one with 2 here. All right, but every one of these values, as you can see, every row is indexed. So every successive time is indexed. That's how computers think. I'm just trying to point out the analogy or the similarity between this and what you'll be doing in MATLAB. In MATLAB, you're going to be doing a loop, and you're going to have to index all the values in an array. All right, so that gives us the time column. Now, you may remember the last thing we built together was this kinematic problem solver. All we were doing there was using a function. We were just evaluating a function, position in terms of time. Well, we're not going to evaluate anything here. We're actually going to approximate all the values in the time, in the position and velocity columns. We're going to approximate it using an Euler equation. Okay? We're approximating everything from the second time step and beyond. The very first time step we actually know. That's the initial conditions. Right? So the initial position, highlight that first box adjacent to time 0. And I'm going to go equals, and just choose the location of the value of x0. Okay? So I'm assigning the first position, which is adjacent to time 0, the value x0. Same with velocity. Assign the first, the initial velocity corresponding to the initial time, assign it v0. Everybody see what I'm doing there? If you have to, go back. You can always go back and run this and take a look again. Try to go slow. All right, so we've got the initial positions here. Okay, let's program the acceleration before we do anything else. All right. Now this is very important, and it's very important to watch closely what I do. The acceleration, remember, is not approximated. The position and velocity are approximated according to those Euler equations. The acceleration is not approximated, although we do put an approximated value into it. This actually is a function that we have derived or gotten from Newton's second law. So the acceleration expression is exact. We just happen to evaluate it with approximated values. All right. So, and by exact I mean, if you go back to the slide, here is the acceleration function right here. And so all we're going to do is do exactly what this tells me to do. First term will be g, gravity, grav, minus all this stuff times v squared. Now v, remember v is evaluated at a certain time. Therefore, I will point to the velocity column when I get to the v squared here. Right? So as I type this in, you might want to keep this equation, keep it in front of you so you see what I'm doing, but I'm going to enter this expression for A and evaluate it at the adjacent, use the adjacent value of V when it comes to V squared here. So go back to here. All right, and here's the first where I'm going to assign this now. So equals, right? And the first term is GRAV. That's what the equation says. Right? Minus drag star rho star area. Right? Look back if you have to. I'm doing the second term, so it's minus d rho a. I'm actually going to multiply it now by v squared. All right, and then I'll divide everything by quantity 2 times m. That's how I plan to do it. It'll look neatest to do it that way. So I'm going to do a star. Now it's the velocity at the same time. All right, and so to have a look. The equation is getting a little bit long. In other words, it's spilling over into the other column to the right as well as to the left. See that? And so I want to choose the velocity box at the same time step, but the equation's leaked over and it's not going to allow me to choose it here. But that's okay. All you have to do is type in F. This box is column F, row 2. All right, so do F2, and it's kind of hard to see, but you can see it put a little, I don't know, what is that color? Magenta? I don't know what color that is. Put a little magenta box, although the field of my acceleration column is leaking over, so you can only see the pink or magenta outline here. Anyway, by choosing F2, it properly programs it to use the velocity at that same time step. So you evaluate the acceleration expression at the same time step. Acceleration is not approximated. All right. Some of you, I can predict you're going to do this because it happens even to Beth's. I'm not belittling you or making fun. I'm just saying some of you will do this, but you will try to to use this Euler equation and the acceleration along with position and velocity, right? I'm saying don't do it, okay? So this has to be squared though, so upward pointing arrow 2. Okay, so that's the numerator of the second term here, d rho a times v squared. Now I divide by quantity 2 star m. Let's go back to here. So I divide that whole thing, so divided by parentheses 2 star m close parentheses. Now look closely at what I have here. And I'm going to urge you also, get in the habit of using a minimal amount of parentheses. Some of you students like to use parentheses like they're going out of style. All right? Look, here's the hierarchical order when computers calculate things. The very first thing that's going to happen is anything in parentheses. So it'll do this. Oops, I forgot a star, by the way. Okay, so anything in parentheses is done first. So it will do 2 star m. Mass, right? There we go. See, it wasn't color-coded when I just had m. Let's do it again. See, I just had m, and it wasn't using the value of mass. And so if I put the ASS in, you got to be careful whenever an ASS shows up. Put that in, and it properly color codes it. Right? So I almost made a couple mistakes. It's okay if I make mistakes. You can see just some of the things you got to be careful and be aware of as you're programming this. But back to parentheses. It'll do 2 star mass first. Right? Then it will raise something to a power if there's any power laws. So it will then take whatever F2, whatever value is in F2, it will square it. Then it will go through and either multiply and divide. So it will actually start here, do this multiplication, then this one, and then it will finally divide by that quantity which already been calculated. Finally, it'll take grav minus that whole product. Right? So you don't need any more parentheses than this. This is perfect. Don't start shoving parentheses everywhere. All right? Use the minimum amount. It's just easier to look at and easier to get correct. When you start throwing parentheses around, you got to find the closing one. Right? So if I hit enter, excuse me, it gives me 9.1 because we haven't started moving yet. Therefore, the second term is 0 if v of 0 is 0, which it is because we're dropping it from the initial position. So it starts out at g. The acceleration will become less than g as time goes on because the ball starts to move, right? So already we kind of know what to look for as a check, for instance, to how I have things, as a check to see if I've actually got it programmed properly. In other words, acceleration should start to decrease, right? We should see it decrease as it goes on. We should see velocity increase and we should see position increase. Okay. Now, I'm going to just, this is programmed for all times now because this is pointing properly over to the velocity column, squaring that at every time step. So all I got to do is drag this down. Now, if I double click it, it will populate all the way down to where the time did. But you'll notice what will happen here. It'll be 9.1 the whole time because it thinks all the velocities are 0. Right? So as soon as we start populating the velocity column, then the acceleration will properly update and be calculated. See, this is looking over here, and it doesn't have anything to change it yet. All right, so let's go ahead and do that. Let's do the next time step for velocity. And this is where, just to show you real quick, let's go back and take a peek. Right. It doesn't matter. Right here. Okay. This is the equation we're going to use. That's our Euler equation. So we're going to do exactly what this tells us to do, and this is why I like to emphasize this notation here. See, in a spreadsheet, this is all visual. This is all laid out right in front of us. I know where the position t plus delta t is. That's the next box down. And this says the velocity at the next box is approximately equal to velocity at the previous box plus a, I got a column for a, don't I? A box at the previous time step times the time step itself. See that? We're going to do exactly what this says to do. All right, so let's go do it. You might want to keep that equation in front of you as I do it, but just watch. Watch what I select. And it really is very easy building this right here in the spreadsheet. So assign this value. assign this. So the velocity at this time step, at the first time step after 0, is going to be the velocity at the earlier time step. So I select the previous box. Equation says add to that the product of the acceleration at the earlier time, and that's this box. See that? I'm just doing what the equation tells me to do. Star dt. And as usual, it's color coding everything so I can see exactly what I'm using in the calculation. See that? All right. And it is indeed starting to increase here. All right. Okay. Now, that's programmed, and all we got to do is do our little double click thing. So move your plus sign over the lower right corner, do a double click, and we're in business. Now the acceleration properly updates. See that? Okay. All right, but now we still have the position to update. Now, remember, and it doesn't matter which one we look back on. We can go, I think, maybe to this one. How about, yeah, remember I did this one. This is just the Taylor series expansion, but it comes up with the same equation. Here's the velocity version, what we just programmed. You can also do the same thing with position. The starting point, of course, is up here. We're expanding the position, right, around some generic time t, and then you truncate it, and it produces the same kind of thing for position, where the position, and we're going to do exactly what this says, just like we did before. Position at the later time is approximately equal to the position at the box above the current one, plus velocity evaluated at the box above the current one, times delta t. So let's do that. All right, so we go here, and so I'm going to set this equal to the position at this next time is equal to the position at the earlier time, so I choose that, plus the velocity at the earlier time. See, I'm using the velocity at the earlier time, not at the same time step, but the earlier one. That's what that Euler equation says. Star dt. Make sure everything's color-coded. It's using the proper value for dt. And if you hit enter, now look what happened there. Didn't we say the position was supposed to start increasing? Well, if I drag this down one more, it actually does start increasing. So what gives here? Did we make a mistake? Why don't you think about it for a moment? Stop the video. Dwell on this. Why don't you go meditate? Go, I don't know. I'm not going to advocate smoking. I was going to go say go smoke a pipe. Stop the video. Think about it. Why did this 0? I mean, the answer's right in front of you, of course, but come back in a half hour after you've meditated. Okay, I assume you've meditated and you're back. Well, look, when we program this thing, if I double click, it shows you how we programmed it and which boxes I used. Look, I used the position at the earlier time. That was the E2. Plus, look what I used. I used the velocity at the earlier time, but it was 0 because this is the initial time. And so if it's at position 0 and it's not even moving yet, then of course it's going to be 0 plus 0 times dt. And this is simply an artifact of the approximation, right? In position, when you do the Euler method, you don't actually get position increasing until the second time step after the initial one. Right? It's just how it behaves. Now, that of course is an error. That the first time step is absolutely not correct. It should be moving. However, once again, if we make delta t really, really small, then that first erroneous time step will only be a very, very small time after it begins falling in. It won't really matter. Okay? Just it's the same reason we're making delta t small, so that we can minimize the accuracy, or not minimize, maximize the accuracy, minimize the error. All right, well, these are all programmed, and all we got to do is do the double click thing. You could go back up to the original one if you wanted to. Do a double click, and it should... no, it didn't do it for me, so my guess is I've got to just pull it back up to one single one, and then do a double click. All right, see that? I had drug it down manually, and it didn't want to do it from there. So I just got rid of those values and started from the one I programmed. All right, and so there we have it. Now you could inspect all these. you see it's doing, at least it's going in the right direction. The acceleration is indeed decreasing. And you know a little something about, you should have some a little bit of intuition what's going to happen. Of course, if you look back at the acceleration term, which is down here, right here, right? This term is constant. That's the acceleration due to gravity. This term, because it's proportional to v squared, the d rho a over 2m times v squared, this term will start to grow as it falls, and it will eventually match this g in magnitude. And when it does that, you will cease to accelerate, right? And when that happens, when the acceleration goes to 0, then you've reached the thing called the terminal velocity, right? And so you kind of expect this. Right, so this is going in the right direction. It's going down. This is increasing. This is increasing. Of course, you know, you can inspect numbers, but we really want to make a graph, right? So I'm going to insert a graph here. So I go to insert, and let's just start with velocity. We could plot anything we want here, but let's just plot velocity versus time. Okay, so I'm going to go up, and I'm going to choose a scatter plot. And as usual, I'm going to choose the scatter and just connect the dots. All right, now it starts out with a blank window for me because I haven't told it what to plot yet. But before I do plot it, just remember that we only have solutions at discrete times. By plotting it, the small points and connecting the dots, it's going to look like a continuous function. All right, so just be aware of that. We're not plotting a continuous function. And as I change delta t, I'm going to explore the parameters a little bit with you, but as we change delta t, you're going to see that you'll see the discrete nature of it. But to start with, if I plot a whole bunch of points, if I plot all 4,000 or whatever points, it's going to look like a continuous function. Just remember we're connecting dots here, right? So I right click, select data, and then I'm going to add a series, and this is where I tell it to plot. And so I'm going to say series name, I'm going to say velocity versus time. And remember how I told you this, if you have a better, quicker way of plotting, that's okay, go ahead and use it. This is just my little dinosaur way of doing it. I highlight the field, series x values. I'm going to use time. Remember, I just grab the first time and drag it down a little bit, and you can see it populates the field with the right syntax. It's going from 2 to 10 right now. I'll tell it to go ahead and go from 2 to, say, 4,000 or so, and we can always change the scale of the plot. Series y values, get rid of what's already in there, and go up and grab the first velocity and just go down a few. You can see now it's using column F, which is the velocity column. So now I go back up to the series x values, and instead of 10, I'm going to use 4,000. And I'll do the same thing for the series y values. Click OK a couple times, and that's what you get. Right? Now, I've got 0.1. I've got a dt of 0.1, and I went out 4,000 points. So I've actually got 4,000 points plotted along here. Right? 4,000 times 0.1 is 400, and you can see we've got 400 seconds plotted. Right? Now, the interesting part's happening way back here, and it doesn't take that long for the interesting thing to happen. And so let's just go ahead and change the scale. Right? So I'm going to go in and zoom in, and I don't know if you remember how to do that. I highlight the numbers, do a right click, we're going to format the axis. This comes up, and let's go, say, I don't know, say 25 maybe. Let's go from 0 to 25. So that's better, right? That gives us a little more interesting thing happening here. All right, and look, it really, if this is a realistic model, which by the way, again, other than maybe those random wind gusts that would move the ball as it falls the full 440 meters at the Sears Tower, just ignoring those random wind gusts, it's pretty realistic. It's not quite, though, and I'll show you that later, but it's actually not bad. And you can see what happens here, that the it's starting to very rapidly approach the terminal velocity here after, I don't know, what, 5 seconds or so. I mean, it looks almost flat here, doesn't it? Out here. So it doesn't take too long to reach terminal velocity. And look, the terminal velocity isn't that great. I mean, it's 20 meters per second is pretty fast. It's clipping right along, don't get me wrong. But it's not accelerating indefinitely. It only accelerates the first several seconds, right? Well, that's the velocity versus time. But we really shouldn't take this too seriously yet, though, should we? Because we don't know anything about our delta t. Is that a good delta t? Is it a good, does that produce a good accurate solution? Should it be made smaller? Right, so we really shouldn't start analyzing anything yet. This looks like the right physics here, at least it looks qualitatively, but we don't know if that's really an accurate solution yet, even though it seems to be acting correctly, right? So we're not going to analyze it too much yet. Right? Now, what I'm going to suggest, now we could play with it, and now let me just demonstrate what happens. What if I make dt bigger? Instead of 0.1, let's make it 2. Right? In other words, I'm going to have a solution every 2 seconds. Now, look what happens. If I change that dt to 2, everything changes simultaneously. All right? Now, especially look what happens over here. So I went from 0.1 to 2. So this is a delta t of 2 seconds. All right? And look what happens here. Now remember, this is velocity versus time. All right? And so what this is saying is that it starts from rest. The velocity increases as you would expect with us falling, something falling. And it starts to level off. All right? But then it suddenly slows down. And then speeds up again. And then slows down and speeds up. That'd be really weird, wouldn't it? If it did that, you think? Answer is yes, that's really strange. And as a matter of fact, we would call this artificial behavior. We don't observe that happening. It does not start oscillating in velocity. If you wanted to make a plot versus position versus time just to see what it looks like, you could add another one. Let's just add another one. Insert. And we'll do another scatter plot, connect the dots here. And I don't know what it thinks it wants me to plot here, but let's go in, right click, and choose the series we want. I don't know what it's got plotted here. Whatever series that is, just remove. All right? So we'll add one here, and I'm going to call this position versus time. And this is going to be the time. And again, I do the same thing I did with the velocity plot. So I just populate it with the right syntax. Go to the series Y values. Now we're going to grab column E here from the initial position down. All right, and let's go back and we'll tell it again to do 4,000 points, which means I'm going to have to change the scale, but that's right. 4,000 points, and you get a couple OKs, and you get this. All right. Now remember, the interesting stuff is happening down here, and so I got to change the scale. Now, of course, with 2 seconds, and 4,000 points, we're all the way out to 8,000 seconds, right? So we really can't tell what's happening back here. So just like velocity, I'm going to go from 0 to 25, right? So let's highlight the x-axis numbers, format axis, and I'm going to change the scale to 25 seconds, right? Which also means I've got to do the vertical axis because you can see it's squished down here. So, but remember, we said if we're dropping this from the Sears Tower, the pavement is only going to be at 440. So let's go, so I think I can get to the vertical axis here. Yep, vertical values. You can go look back in the video and see how I did that. Let's go from 0, and what did I say? Let's say 450 meters. Right? And let's get rid of that thing, and then have a look here. So remember, I said, I mean, we could look this up again, but I think I'm right. I think that the Sears Tower, I think the observation deck's 440 meters. Well, yeah, look, let's actually change the vertical scale here to include negative values. Let's go down, say, minus 10 or so. Okay, and the reason I did that is because, look, this is really weird. See what happens here? Starts at 0, I changed the lower limit here. Starts at 0 and it actually goes negative. That means it goes up. When I drop it, it actually goes up a little bit. So clearly, that's weird, right? So the velocity is weird enough with its oscillations, but certainly the position is just impossible. That doesn't happen. If I drop a ball, it doesn't go up first and then go down. Right? So obviously there's something funny going on here. The problem is delta t is not an accurate value. That's not producing an accurate solution. You can help things a little bit. Now, one thing we can do here, let me zoom out. And let's zoom out even more. As long as you can still see the numbers. It might be, oops, I don't want to do that. It might be instructive just to somehow put the position versus time underneath the velocity versus time. You can change the size of these. Let me pull this out a little bit, kind of like that. And let's put this one up here. I'll go down and grab it. And we'll make it about the same size. This way you can sort of do a comparison. Well, not sort of, you can do a comparison, I guess. And zoom maybe a little bit. Alright, so you can see what's happening with both the position and the time graphs. It's cutting off some of it, I guess. Well, maybe not. No, I guess it still is auto-scaling in that upper one. Let's change the scale back real quick. No, why is it doing that? Oh, it's still there. It's just, this is the, okay. It's just the labels it's using. All right, well, what I want to do, let's systematically lower delta t now. So watch what happens. I'm going to go from 2 to 1. That's better, right? It doesn't, we could zoom in. Might still be acting weird here, like dipping below, but at least those oscillations are gone in the velocity. Let's go from 1 to 0.5. That still changes quite a bit, doesn't it? So, especially watch this. See this area here? The curved part of the velocity versus time? Watch what happens if I go back up to 1. That's actually changing significantly, isn't it? All right. So we don't really quite know what's happening. In other words, we don't really know what is really an accurate value yet, although certainly the lower the better, right? So if I go to 0.1, and again, if I go back to 1, I'm just changing delta t, go back to 1, and now watch what happens in the velocity, especially around this little hump here. When I go back to 0.1, hit enter, look at that, it changes pretty dramatically. What happens if I go to half of that value? In other words, not from 0.1 to 0.05. Okay, ready? I'm going to hit enter. I saw it move a little bit. At least on this scale, it moved a little bit. So if by changing delta t it causes the solution to change, we have not reached a sufficiently small delta t yet, have we? There's still artificial behavior that is appearing because our delta t is too big. Right? It's not accumulating error very well. So what if I go to 0.01 from 0.05? I could barely see anything. So I think you would all agree, and let's just do the dramatic value here. We'll go back to 1 for delta t and hit enter. From there to 0.01, from the value of delta t of 1 second to 100th of a second, it looks like it's converging toward this point and doesn't move much anymore. All right, which in itself is a bit of a hint. That's how you go about finding the delta t, or a good approximate value, if you watch the solution converge. That's if you don't have anything to compare it to. But let's do the following. Let's add something to this graph. All right, I'm going to move this graph over. And actually, let's add another column. And that's why I did this integral back on the slide for you here. Let's go down to this one. Remember I said you can actually integrate this thing as long as you're pretending d is constant, which we are. And look, let's plot this thing here. let's actually add that to the graph. All I'm going to do is use the time column, use those times to evaluate this function of t here. This is the exact solution. I want to make a comparison between this exact solution and my numerical solution. So let's do it. All right. So first of all, we got to add the column. I'm going to call this v. I'm just going to label it v exact. Right. And now I'll just put the function in here. So once again, we got to look and see what we're doing. The first thing is the square root 2mg over d rho a. Right. So let's do what it says. Equals sqrt, RT, that's how you get a square root. Right? And I got to look back. No, it's 2 times mg divided by d rho a. Now we've got to use our names as we have them defined. Okay, so it's 2 star MASS, right? It puts the little color code there, so I got it right that time. Star GRAV. Remember, if you've defined the variables different than the equation, don't let that trip you up. Don't put in mg and then wonder why it doesn't work. We define those as mass and grav, remember? All right, that's square root of that stuff. Well, actually, let's do divide by. And since it's divided by the whole denominator, it's going to be the quantity. D rho a, I think. So it's drag star rho star area. And I need one more parentheses to close. Now watch when MATLAB does this. Octave doesn't do it, but MATLAB does it kind of nicely. Watch the parentheses closely here when I put my next parentheses. You see it momentarily highlighted the one it was closing. And to see it again, you just backspace, put it in again, and it highlights it momentarily. All right, that's the first term. So I'm going to do then star. So it's the square root of that stuff. Star the hyperbolic tangent. The spreadsheet actually knows what that is, believe it or not. So it's going to be TANH of, all right, and let's look back here, a square root again, but you'll notice the t is not in the square root. So it's the square root of this stuff, so let's do that. Okay, so it's going to be SQRT. We've got to really keep track of parentheses here. SQRT of, and so the numerator is d rho ag. All right, so it's drag star rho star area star grav, right? Divided by quantity 2m. Right? 2 star mass. Right? Looks like that. Okay, but I need to close the square root now. Like that. All right, so I close the square root. Now I just multiply that by the current time. Okay, so I go star, and then I go over and choose the current time. That is the time at that exact same time step. So I choose that guy. See that? Now, this final parentheses I put here should momentarily highlight this one right after the hyperbolic tangent. Let's see if it does. Yep. So I think I've got it right. So that looks like a really bad, terrible equation to have to deal with, but it's not that bad. You can see it didn't take me that long, and I was just very careful as I did it. And you can see it color codes it for me using the right variables and all that sort of thing. Again, we're just evaluating a function here for this exact. Starts out at 0, and that's nice because that was our same as our initial velocity condition, right? And all I do now is grab the thing and do a double click. All right. Now you can inspect this and compare this with this, or you can make a plot. Let's just go ahead and make a plot. All right. Let's add it to my velocity versus time plot. So I go to select data, right click, select data, add a series. All right, and I'm going to call this v exact versus time. Okay. The series x values are time again. So go over to the time column, grab the first one, and go down a little bit. Series Y values will now be the new column I just defined, starting at the initial value. And as we have done in the past, we're not going to look at all of them, but go ahead and use all 4,000 points. A couple OKs. And now we have it plotted, although you can't quite tell, right? We could add a legend to this if we wanted, but what you're actually looking at is the solutions are overlapping. One of them's red, in other words, one, I'm not sure which is which, the v exact or velocity is red, the other's blue, but we can separate them if I make delta t bigger. So let's go back to delta t of 1 again. And all I do is go over to the control panel and change it to 1. And now we know which is which here, right? Remember, it's the computational solution, the velocity, that moves up. The little hump moves this way. It doesn't converge. It goes the other way when I raise delta t. So that red is the exact solution, right? And you can see what happens here as I change 1. Let's go to 0.5. See that? The blue's getting closer to the red. If I go to 0.2, closer yet, you can still see a little blue though, right? I mean, why bother? Let's go all the way down to 100th. And it sort of disappears, which means it's really converging toward this exact solution. And maybe, just maybe we can get away with approximating that exact solution with a delta t of 0.01. Right? Of course, you can always do the following. Let's zoom in just as one last little thing for this video. The first guided activity, which is I'm going to make you do this in MATLAB, this very thing. So you've got a guide. I'm not going to make you do anything you're not already doing, but you're going to use MATLAB to do it. Okay. I guide you. There's several exercises that'll be part of that first guided activity, and I'll guide you through exploring these things that I'm playing with right now. Right? But one more thing to look at, and then we'll call it good. Let's just zoom in on this little hump. Interestingly, if we go back to 1, once again all the way back to a delta t of 1, interestingly the solution seems to match pretty well out here still. See, the red and blue are overlapping out here for large times, and for very early times they seem to overlap well. But starting about here up to about here, see, they just don't match well. It's this middle area that has troubles here, right? So let's zoom in. And what I mean by that, let's go back to maybe 0.1. And let's zoom into this little box here. So let's go, say, I don't know, horizontal, I'll go from 2 to 5. And maybe 15 to, I don't know, 21 or something like that. All right, so let's change the scale. Okay, so again, horizontal will go 2 to 5 seconds. And then the vertical, would I say 15 to 21 or something like that? Vertical scale will go 15 out to 21. Okay, and then we can get rid of that. All right, so look, this is just zoomed in. And so even 0.1, you may remember, that looked pretty good, didn't it? Well, in this scale, it doesn't look so good suddenly. The blue is still deviating. There's still a discrepancy between the blue and the red one. The red's the exact, the blue's the computational solution. Let's go back and look at 0.5 again. See, even worse, right? If we go to 1 second, okay, even worse yet. See that? All right, so let's systematically go back down. 0.5, it's approaching now. 0.2, oops, I changed the wrong one. Hold on, somebody call timeout. I don't want to change V0. All right, go back up to the DT. 0.2, better yet, see that move? 0.1, better yet, it's converging, isn't it? It's converging toward the exact solution. 0.08, better yet, 0.05. I can still see some blue there, see that? but it is definitely converging. Let's just go to 100th, 0.01. Now on this scale they seem to overlap, but you know what? I could zoom in again. Let's say we zoomed in on this rectangle. And you would actually see them split apart again. So once again, we have to determine what is the value of delta t that we can deem it to be an accurate solution. Probably for our purposes here, I don't know if, I don't think you'd be able to, I mean, let's say you're doing the experiment. You probably wouldn't be able to accurately determine the speed of the ball any better than the difference you're seeing here anyway, right? So I'm sure 0.01 is just a small enough delta t to get away with a good approximation, right? Of course, there's no reason. I mean, you can go to 0. My laptop can easily do this if I make it 1,000th, right? Now, remember, we've got 4,000 points plotted. And if I go to 0.001, that means I only end up with 4 seconds of model time. So if I want more seconds, I got to go drag down more. Okay? All right. Well, that's all. That's all we're going to do on this. You can play with this more here. What I've done is we've built the model. We put all the parameters in the control panel. We defined all our columns. We populated them all with values that are stored here. In the spreadsheet, that's analogous to storing values in the random access memory as arrays. We programmed everything, we made some plots, and we even explored the accuracy of the model compared to the exact solution. All right, so what I've found useful for students, by the way, it's nice to see this, and even if you've built this along the way with me, that's good. Why not get away from this now for a little while, and maybe in a few hours or maybe tomorrow sometime look at those slides and open up a blank spreadsheet and try to do it on your own again. Try to build the model based on Euler. It'd be good practice. Students who do this benefit greatly from it. Just this simple little, just doing it again, even having seen it done, just thinking through it again really can be a good experience. All right. If you have any questions, holler, and let's call it good. This is El Gallo or Der Große Hahn, whichever one you want to refer to your honorable host as, signing off. And until next time, may the force be with you.